Okay. Hi, my name is Dennis Ray, and this is my presentation on the hidden layers within image upscaling. So, last week or last concept map, I covered image upscaling, which basically is the process where you take an image and you enlarge it using machine learning. So, the reason why it's not as simple as just making it big by zooming in is because as you grow bigger, the pixels enlarge and there's a lot more empty space between them. So the picture would become blurry. So what this machine learning does is it fills in the gaps between the image. And so even when you enlarge it, upscale it, it still is a clear image. And so last week we covered the generalization of how this worked. This week we're going to cover the hidden layers within it. So let's say that we start with a image size 256 by 256. And so generally the first thing we'll do is break the image up into some kernels. And the kernels will give us the presence and location of directional edges. So like the edges within an image are where like the colors change drastically. Like say you have like a black shirt and then suddenly it becomes blue. So the image, so as a human, we could guess that it's changing from a person's shirt to a sky, but an image wouldn't know that. So that's where like edge detection comes into play. So after we break up the image into these sections, these kernels, we run it into the neural network, and a small section of the input image is we put it into the first neural network, the first convolutional layer, and this image is collected from the larger image using a small square window. And so the first convolutional layer contains the most filter maps, and so it'll take it and then it'll filter out. Yeah, and then the outputs from those filter maps are then re-put onto a higher dimensionality through the first two dense, fully connected layers. And this output is further processed by the next two convolutional layers, and these layers and some features from these first two layers are also present in other ones. And then the final output layer, output image, is calculated by a linear Gaussian layer. So this is an equation for bicubic interpolation function, the equation that calculates the inputs. Each sample within the dataset is low and a high resolution image pair. So we have a low, we have like a low, which is what we're gonna get, and a high, which is what we want. So the low resolution, the X input, was created by downscaling a high resolution within a certain factor. So, and while the desired output Y was the original high resolution image. So the X input, as I just said, is the the upscaled image, and Y is the original one. And the data was normalized to have zero mean by calculating um, global mean and to unit variance by dividing through the standard deviation of the data set. And so this is a image of some of the hidden layers. So there are some maximum constraints that enforce a absolute upper bound on the weight vector's magnitude for every unit in the layer, which stops the network's weight from exploding if the gradient update is too large. So, like, if the descent of the gradient, like the slope that we calculate through backpropagation and gradient descent, if that slope becomes too large, then that's what the norm constraint stops. It doesn't let it be too big. And these constraints are used in every layer except the final Gaussian layer because that's calculated in a different way. And this is another in-depth view of the hidden layer. So that's our input. Then you run through. That's the first two, which makes it project onto the third. Then you keep running it through, and then you apply your Gaussian function and you get your output. So L2 regularization penalizes the network for using large weight vectors, which is set by the parameter, I think it's rho, and is known as a regularization strength. And this regularization strength is also included in the cost function. And it tries to keep the weight small in order to minimize the cost function because we're looking for the derivatives, right? And a derivative is defined as like what a small change in x will do. So the weights have to be small in order to have accurate derivatives. And the convolutional layers in first two have mild regularization applied, and the other densely connected layers use a stronger value. And yeah, these are some of the results of image upscaling. This is the original. This is after it. This is bicubic interpolation, which basically just uses pixels around it to generate the image. And this model is what happens after you use all the hidden layers in machine learning. So it's quite similar to or the original, at least more than the bicubic. Yeah. So this is this is kind of what Mr. Corrado was talking about, like a flow chart of how this entire process works. And if we were to define, like if this would be like if I created a hidden layers for this image upscaling, this would be how he wants us to think about it. Like we go step by step by step, and then we make sure that everything we do is running smoothly, and then we move on to the next step. So image upscaling can kind of be compared to a microscope from science. So light reflects off an object being viewed under the microscope and passes through the lens, and it bends toward the eyes, and this makes the object bigger than it actually is. Right, which is what image upscaling does. It takes an image and then it makes it so that it's bigger while maintaining the same quality our eyes like to see. So image upscaling uses machine learning, or more specifically neural networks and associated gradient descent and back propagation to do something similar. Instead of making the object larger, it fills in the gaps around the image and gives a clear picture that our eyes are able to see. The hidden layers would kind of be represented by the mirrors in the microscope, right? We can't really see what's going on, but if we were to take apart the microscope, we can adjust them to get a better image. Yeah, image upscaling is used a lot in web browsers, image editors, image and file viewers. Like image and file viewers would be like you download an image, say off the internet, and you save it to file. You open the file, and there's like the control plus function, and that's this image scaling at work, upscaling. And upscaling is normally performed in real time, and the output signal is not saved generally. And yeah, thank you so much for watching. This was my presentation on back propagation. I hope you learned something, and yeah, thank you.